So, hello everyone. What we're going to do now is to talk about time evolution, which now is going to be a bit beyond of what you have seen in your undergraduate course. So, I hope you enjoy it, and I'm going to do this in a bit more detail as well, because so far you have focused in your whole life in on time independent Hamiltonians. And we're going to consider something that is more general. Okay? So let's do it and let's get started. Time evolution. And if you remember, this was one of the postulates we discussed in our very first lecture. So this was postulate 2, which stated that the evolution of an isolated system is described by the time-dependent Schrödinger equation, which is something we all are familiar with, where H is the Hamiltonian operator, which is a Hermite operator specifying all the full dynamics of the system. So we're going to see a few more interesting things here. And in fact, what is very nice, let's have a look, mathematically speaking, at this time-dependent Schrödinger equation. Can you see it is of first order in time? Can you see that? You have here IH first derivative with regard to time of psi, and then here you have the Hamiltonian and psi. So what does this mean? This means that if you know the initial state of the system, then psi t may be in principle determined at any subsequent time. Mathematically, that's what we have, right? If you have differential equation of the first order. So this is actually nice and is also good news for us, because that's what we're going to use, and we're going to define time evolution operator. So we're going to start quite abstract, and we're going to consider a state vector psi t, and this state vector was evolved from psi t naught. And we do this evolution according to the time-dependent Schrödinger equation, right? It has to be, because this is the equation that is governing the evolution of an isolated quantum system according to all the postulates we have seen. So you want to take the system from a state psi t naught to a state psi t. And we can do this in this way here. And what we use here is U, which looks quite mysterious for those who are not familiar with it. And normally this is not a formulation you see in the graduate course. This is what we call the time evolution operator associated with the system. So you're taking a system from psi t naught to psi t. Now, what are the implications? Well, we're going to solve a few things, and we're going to discuss the properties of this guy. Okay, because it has some properties which are quite important for us, and we do need to have a look at the properties. So the first one is, no, this is wrong. Here are the properties. Is that if you write u t naught to t naught, so you want to take your system from a certain time t naught to the same time t naught, this is going to be the identity operator. It's fair enough, it shouldn't change, right? Now, the system hasn't evolved because the time remained the same. It has to be like that, otherwise there is some kind of inconsistency. If you also want to take your time or your system from a time t naught to a time t, what you have is first you take from t naught to an intermediate time t dash, and then from t dash to t. So you pretty much define some kind of intermediate evolution operators. And the total evolution operator is some kind of composite operator built up using those guys, those intermediate time evolution operators. And also we can say that the inverse of taking the system from t dash to t, which is characterized here by u minus 1, is if you evolve it back from t to t0, which is also clear. It has to be this way. It's like you are devolving, not evolving, bringing back. So, and we have that UTT naught satisfy the time-dependent Schrödinger equation. Has to be like that. And I'm going to show you that this must be the case. Because if it doesn't satisfy, what on earth are you evolving here? So let's prove that. If you tell me I don't believe you, let's have a look. So you have then the time-dependent Schrödinger equation, which is IH bar G dt psi t equals to H psi t. One thing that I can definitely do is here I can insert psi t being equal to u t t naught psi t naught, right? After all, we have evolved this equation, and this wave function, this state of the system that we have evolved, not a wave function, it's a state of the system, more general, has to obey certain rules. And we have postulated, okay, you have psi t naught, which is your initial state in state space, scat psi t naught. You evolved from t naught to t, and you got psi t. So an operator there is modifying the system, is making it evolve. If we insert this in the time-dependent Schrödinger equation we have, then that this is going to give IH bar d dt u t t naught psi t naught, and on the right hand side we have H u t t naught psi t naught. Get. So far, so good. We can also rearrange this And we can say, when we apply this derivative, look, that only this guy here is depending on t, right? So let's write this, and we have then IH bar d dt u t t naught minus h u t t naught psi t naught equal to 0. So basically, I applied this derivative here because it's with regard to t, and I brought this guy to the left-hand side. So this was the rearrangement that I've made. Now, I want this to hold, and this is important, I want this to hold for an arbitrary. This must hold for an arbitrary psi t naught. Why am I saying that? Because, well, we'll have also the trivial solution, right? If this is equal to 0, either this whole bracket can be equal to 0, or this guy can be equal to 0. But then you have a very, very, very specific cat, and we want this to be general. And we are saying that this then must be an arbitrary psi t naught. Otherwise, it's not much help, right? So this means then that IH bar G dt U T T naught minus H bar U minus H, U T T naught is equal to 0. And it's very nice because you can really see that this time evolution operator, which is something very mysterious, satisfies, and it has to satisfy time-dependent Schrödinger equation. Another thing we can say about it is that it is unitary. And this is extremely, extremely important. Why do we care? Because unitarity is going to guarantee that the norms and the inner products are preserved. Just remember our previous lecture when we were talking about unitary operators, and we have shown that if the operator is unitary, the norm has to be preserved. So we can definitely have a look. If you don't believe me, we can check it out, but it is pretty much a specific case of what we have seen in the lecture related to unitary operators. But let's check. So we're going to write a cat psi t, which was evolved using the time evolution operator u from t to t, from t naught to t, and originally we had psi t naught. Now, how about the associated bra? What does it give me? Well, if you look at that, we know how we have to write. We have to transpose, and we have to get the we have to get the U dagger, and we would like to calculate the norm. So if we calculate the norm of these wave functions, which is going to be then psi t bra in a product with psi t cat, you find that this is what we have to use, right? So we're going to have psi t naught u dagger t naught u t naught psi t naught. We want this to survive, and we want this to be preserved, right? So what do we do? The only chance we have to achieve that psi t, so the norm of this state vector at the time t is going to be equal to psi t naught, which is the norm of the state vector at a previous time t naught, is if u dagger t naught u t naught is equal to the identity operator. So if these guys here are the identity operator, otherwise it would change. And this condition is in fact the condition of unitarity. So this is telling me that u dagger t naught is equal to u minus 1 t naught. And if you would like to prove this for other systems, for instance, if you want to use this to calculate an inner product and show that the inner product is also going to be invariant upon time evolution, you proceed in pretty much the same way. Okay, same argument can be used in the case of inner products. Okay, so we are going to have a look at a very specific case, which is when H is independent. So this is what we call conservative systems, and we have this situation a lot in quantum mechanics. So H is time independent. These systems are very convenient. I mean, for instance, in my field of research, I never have this because I'm using huge fields. But if you are lucky enough in your life, you will have time-independent Hamiltonians in whatever problem you're looking at, and they're going to simplify the dynamics a lot. So first thing first, I want to show you what happens to the time evolution operator. So I'm going to start looking at the time dependent. Schrödinger equation. And in the general case, we have something like this. Not caring about anything, not making any assumption if this Hamiltonian and if this time evolution operator, which corresponds to a certain Hamiltonian, is explicitly time dependent or not. I'm just saying, okay, this is the general case. And we have seen that the time evolution operator has to satisfy the Schrödinger equation. So you have something like that. Here you have the time derivative of this operator, and here on the right hand side you have the Hamiltonian, which may be time dependent. We don't know. This is, as we have just stated, this is first order differential equation in time. So we can integrate this, right? We can rearrange this and we can write something like this: du t t naught u t t naught, and here we have from t naught to t h tau to tau. We can do that. Okay, and this is going to give me natural logarithm u t t naught equals to minus I h bar t naught t h tau tau. Now, this is a bit curious. You can say, okay, so I have to include something else. I'm doing this a bit quick and dirty, but my interest here is to show you the general form of this time evolution operator. But in real life, you have to be careful with something we call time ordering. And we're going to see this in more detail when we discuss chapter 4 later on in the course. But for the moment, what matters to us is that you have u t t naught is tau, which is something that indicates the time ordering, exponential minus I divided by h bar t0 t h tau tau. So we have an expression for the time evolution operator, which a lot of you will find maybe in your research projects or in scientific papers, and this can be quite useful. But we are concerned now about a very particular case, which is if our Hamiltonian is time independent. So we're going to have a look. So in this case, it doesn't depend on time, which means that we're going to have this expression if we solve the time, the differential equation to first order in time, which is the Schrödinger equation. Sorry, forgot this. And you find that u c t naught is e minus I h bar h c minus t naught. Which you see simplifies a lot because you don't have this business of time ordering, you don't have complicated integrals. So in fact, many times when you want to compute things, for instance, we're going to see time-dependent perturbation theory, this is absolutely useful. And we're going to assume now that we are dealing with stationary states. which say you have this time independent situation for a Hamiltonian, and the system is initially in an eigenstate. So we assume first H is time independent, and then we have that the system initially in an eigenstate of H, which means then that psi 0 is psi n, and this guy here is an eigenstate of H. If you can write an eigenvalue equation for H, you are in a situation where your system is conservative. So strictly speaking, you don't have any explicit time dependence in your Hamiltonian. So we know then, if this is the case, that this is an eigenstate of H, that H applied to psi naught, where naught is the initial time t equals 0, is going to give you this eigenenergy. So this is the eigenenergy corresponding to this eigenstate psi n. Correct? Now I would like this to evolve. So let's evolve. We're going to have the following. Psi t is going to be u t0, psi 0, which is the eigenstate. So we're going to apply, we're going to say, Hamiltonian is time independent, remember? So this is exponential minus IHT divided by H bar, psi 0. And from here we get exponential minus IENT divided by H bar, psi 0. So you see what is happening here. This is just a phase. Huh? Some people say, oh, you're doing something, this is just a phase. But in this case, this time evolution operator, because you start from an eigenstate, this is just a phase. So I'm going to write that, please note, in this specific case, the time evolution operator is just a phase. And since, if you have, for instance, EI5 psi, so you have, again, just a phase, and psi describe the same physics, we can then say that the state psi t is stationary, meaning that psi t is going to be equal, when you calculate whatever, e I phi psi 0, which is an eigenstate. So whatever you calculate is not going to change. Now we know also that what matters to us many times are phase differences, right? If you had, for instance, a coherent superposition of eigenstates at the very beginning, then you have to be a bit careful. So in general, so this was, let me make this point A, and I make like a point B here. And I say that in general, any cat psi t can be expanded into eigenstates of H. In this specific case, that H is not time dependent, okay? Meaning we can write psi t like that. If you are confused, I have just used a closure relation here in terms of these basis vectors. And when you apply this here, you get these coefficients and you get this guy, okay? But I can write it like that. It's good to try it a bit at home if you're not convinced. It's a good exercise. And since we can say that psi n psi t is equal to psi n u t t naught psi t naught. So you see what let me write it a bit better. You see what I'm doing? I'm writing this, or I want to write this in a way that I take into account this time evolution. So I'm going to write psi t as u t t naught psi t naught. Okay. Now we can also say that, which is the case, if H is time independent, then we're going to have that psi n psi t is going to be bra psi n e to the power I divided by h bar h naught t minus t naught psi t naught. So what I have done here is I applied the expression that we have derived. And I'm evolving this from t naught to t and considering our Hamiltonian to be time independent. Now we can apply this to the left, right? And if we do that, we get e minus I e n divided by h bar, t minus t naught, psi n psi t naught. And if we insert this back, we're going to find that psi t can be written as n e I am so we are writing this in terms of stationary states, and a key advantage is that this expression here is going to be time independent, so it's going to remain the same forever. And this can be very useful if you are dealing with a complicated problem and you want to study, for instance, wave packet dynamics or so. And all your time dependence is going to be here on these guys. Okay. And this is useful not now that phase differences must be taken into consideration. If you didn't have the sum, you wouldn't have to bother, because you have if I phi and phi, they give you the same behavior. But you have here coherent superposition, you have a sum, and you're going to have phase differences. So they must be taken into consideration when you are studying the system. However, the big advantage of this, of writing it in this way, is that you simplify a lot the study of the time evolution. So it's a very convenient basis if you can do this. Because first you're going to have time independent overlap integrals, which are these guys here. When you compute this psi n with psi t naught, they're not going to change because psi n are stationary, psi t naught is what you had at the beginning. So you're going to, in practice, have to calculate this in a product as some kind of overlap integral, which is going to be stationary. So this is beautiful. And you're going to have that all your time dependence is going to be here. Ah, no, I didn't want to erase it. It is time dependent. It's going to be in this phase. So time dependence in exponential factors. All of it. If you were using another basis, it could be that these would change with time, or maybe these would change with time. You don't know what is going on. And here, no. Here you know for sure. So more details on unitary time evolution you are going to see later in this module, and this is quite nice if you're looking at it in conjunction with time-dependent perturbation theory. So I hope you enjoyed it, and see you in the next clip.